the next couple of minutes, I will be presenting on plant-wide optimization using process digital twins. So previously Rakesh ji explained the need for plant-wide optimization, but now I will be explaining one step more, particularly in the context of production planning, how this is useful. So the outline goes like this. So I will be covering the important challenge that currently the pulp mills are facing in the context of production planning, and how the plant-wide optimization can help address these challenges with few use cases, followed by ABB's solution with respect to plant-wide optimization, and then conclusions. So as we are aware that pulp mills have a complex network of operations, so it is very difficult to manage the production for the entire mill, because some of the processes are they are kind of continuous, most of them are continuous, and some of them are batch type, and some of them have takes long time. Means dynamics will change from process area to area. Say batch digesters can take long time, while brown stock washers can run in few minutes. And a disturbance in one of the process area can impact other process areas very easily in a short time as well. So as already we have seen in the previous presentation that optimizing each section individually cannot address this issue. To improve the overall mill performance, we have to address this by means of overall mill perspective. We have to consider the entire mill as a one system. So coming to the current state of pulp mill operations, if you see, so in particular in the context of production planning, most of them are manually coordinated, means that they are mainly dependent on operators' experience, and also the decisions are taken area-wise. Means sometimes these decisions can be complementing, but sometimes they will be conflicting as well. Also at the same time, some mills will be using spreadsheet-based calculations, using mass balances. These are a little better, but still cannot respond dynamically to real-time changes, and also lack prediction capabilities. So ultimately leading to suboptimal solutions. So there is a necessity for plant-wide optimizer which can optimize all the process sections simultaneously to improve the overall mill performance. So in this study, we are coming up with a plant-wide optimization for pulp mills, where we are developing this solution in two steps. Step one is basically developing a process digital twin for entire pulp mill using first principle based models. So once we develop this digital twin, we use this for the plant-wide optimization, wherein we formulate the objective function such as maximizing the throughput or balancing or meeting the demand coming from the paper section, at the same time respecting the constraints on the process, say process capacity constraints, or even the inventory constraints or resource availability constraints. So basically, in the back end, we will be solving a nonlinear programming problem that calculates optimal production flow rates for each of the sections in the pulp mill. So what is a digital twin in this context? So in this study, we consider three important characteristics to call it as a digital twin. First, the model should be the model fidelity. So it can be of high fidelity, rigorous model that can capture all the dynamics, reaction kinetics, everything, or it can be a medium fidelity, steady state mass balance model also, or it can be a data-based models, or a combination of all these to get the proper accuracy of solution and as well as computational efficiency. Second thing is, once we develop this model, if we don't integrate this with the real-time data, the use is limited. So it has to tightly integrate with the real-time data. So basically, whether it is online or offline, or even the information from the MES as well. And also, once the model calculates or recommends something, it has to be displayed, communicated back to the operator. So what we have done in this study, we have developed a comprehensive set of model library for the particularly catering the pulp mills, wherein we have models for digesters, ground stock washers, or reactors, and all of these are developed from first principles, means physics-based models that work on material balances and also captures the important dynamics and as well as in the lumped effect of reactions as well. So again, these models are basically can cater different types of pulping processes, craft pulping, acid pulping, mechanical pulping processes, and also these are modular in nature. One can drag and drop and can perform unit level modeling to plant level in a very short time. And once we develop integrated model, we will tune it with the plant historical data, and then it can be used for water analysis. As you can see from here, that a digester breakdown, how it is going to impact the important inventories in the pulp mill. Again, this model can be even utilized, this digital twin can be utilized even for the plant-wide optimization, which we are doing in this study. So for the optimization part, we have considered a craft pulping process to study in this example. So wherein we have developed an integrated model for the craft pulping process, considering all the important sections, right from cooking to bleaching in the fiber line, and as well as evapes to causticizer in the recovery line. And it also has 7 important buffers, 7 important storage tanks, which I have shown in the blue color. So these are the actual buffers or the degrees of freedom optimizer manipulates to coordinate the production in the context of production planning, to meet the demand coming from the paper section and also to ensure the constraints are met. Here the objectives that we have set is meeting the demand coming from the paper section and at the same time respecting the constraints on the process delays as well as process capacity constraints and as well as inventory constraints. Basically here we have considered a planning horizon of 48 hours for this example study. The first use case that we have considered is variable demand from the paper section because it's a planned maintenance activity. And then the optimizer task is how it is going to address this variable demand by coordinating the productions across all these important sections without disrupting or without interrupting the actual process. As you can see from this diagram, there is a demand variation from the paper machine that the demand is going to 0 between 28 hours to 44 hours of simulation. Basically because of which there is an accumulation happening in the bleaching storage tower, which you can see that level is increasing in hitting the upper limit. So the optimizer is taking proactive action. It is even reducing the production rate of bleaching section quite few hours before to ensure that the level in the bleached pulp storage not to go beyond the upper limit. Similarly, as the bleaching production rate is reduced, it is impacting the accumulation in the O2 deliquification and it is hitting the upper limit. So again, the optimizer is manipulating the production rates of deliquification. Similarly, it is even manipulating the production rates of cooking section as well. So one can notice here that to address a planned maintenance activity in the paper section, which is going to happen around 28 hours of this simulation, it is reducing the production rates in sync quite few hours before, right from the cooking section onwards, to ensure that the inventory levels not to go beyond upper limit or not to go below the lower limit. So in a similar way, once it reduces the production rate of digester, it also impacts the weak black liquor tank accumulation, which is decreasing. So ultimately, the optimizer is manipulating the evaporator production rate as well. So coming to the recovery boiler and cost sizer, these production rates are not manipulated because the inventories are still away from the high and low limits. So overall, one we can see that this plant-wide optimization is proactively taking actions to address this variable demand coming from the paper section. And for example, if you address this disturbance using manual coordination, there is a most likely that some of the inventories, either overflow or underflow, can even lead to stoppage of the machine. Similarly, we have done another use case where there is a constant demand coming from the paper section, means that the pulp mill has to supply a constant pulp to the paper section, while at the same time there is a planned outage in the cooking section. So the optimizer, how it is coordinated in the production rates, you can see here. Interestingly here, the optimizer is not only proactively taking actions, it is ensuring, strategizing, it is keeping the buffer in the washed pulp storage to the upper limit even before the outage is going to happen, so that there will be a continuous productivity from the fiber line, because there is a hard constraint from the paper section that we have to meet a constant demand. Along with that, it is also manipulating the production rates of delignification and bleaching in order to ensure the inventory is not to go below the low limits. Similarly, manipulating evaporated production rates, since the dynamics are slow in a strong black liquor tank and as well as white liquor tank, it is not manipulating cost sizer as well as recovery boiler productions. Of course, there is a change in the white liquor tank level because the registered production rate is down. However, still that level is still far away from the upper limit. So in this case, compared to use case 2, optimizer not only taking proactive actions but also strategically keeping the buffers to the limits to ensure constant production to meet the demand coming from the paper section. So in the interest of time, I will skip the use case 3, and with this, ABB has developed a solution called ABB Ability Plant Optimizer that has 2 modules called, one is pulp tracker that tracks the pulp movement, as the name implies, it tracks the pulp movement right from the digester still up to the end of reactor in the fiber line, along with the quality parameters. It also helps in diagnosing, for example, if there is any quality deviation in the pulp. And also it helps in coordinating rate change management. And the pulp optimizer, as you have seen already, it actually does economic optimization. It also has a predictive capabilities, and it can be configured for multiple fiber lengths as well. So this slide shows how the data flows in the plant optimizer. So as the optimizer has to receive the real-time data, so the basic data flows, consistencies or quality parameters that flows from DCS to the plant optimizer. On the other hand, it also receives information from the MES, where what grades to be produced, how much quantity of each grade to be produced, because the plant optimizer realizes this MES plan or the big horizon to the day-to-day operations in the plant. And also it receives different recipes information, particularly for coordinating the grade change information, grade change in the pulp mill. And what are the optimal set points calculated by the plant optimizer, they will be sent back again to the DCS to display to the operator, and also they can become set points to the APCs as well. So with this I conclude my presentation saying that plant-wide optimizer can help to address the gap between manual coordination as well as versus mill's theoretical potential. And you can see that in the study, digital twins can enable this kind of plant-wide optimization. And from the use cases, you can also see that plant-wide optimization can handle this kind of disturbances in a very effective, smooth way, which can lead to improved productivity. And finally, the optimizer takes actions proactively rather than reactive, and also it considers system-level optimization rather than unit level. Yeah, that concludes my presentation. Thank you.
Thank you, Mr. Mekapati.